Lesson 15.3, Task 1. Analyze special products. Special products of binomials have predictable patterns that can be applied when multiplying the binomials. Algebra tiles and area models can be used to represent special products of binomials. The algebra tile diagrams show products with binomial factors. All right, so diagram 1, okay. So we've got x plus 1 and x minus 1. So let's kind of represent what these are. So this is x plus 1, and this is x minus 1. All right, this one would be x plus 2, and this one's x minus 2. So you can see it's the same binomial, different sign in the middle. Same binomial, different sign in the middle. Okay, so there's a pattern here. All right, and diagram 3, we've got x plus 3 and x minus 3. So again, same binomial, different sign in the middle. So it says complete the table to represent each diagram as a product of putting the binomial factors in each product in the first row and the polynomial in standard form in the second row. All right, so diagram 1, we did look at diagram 1 and discovered that it is x plus 1 and x minus 1. All right, so when you multiply this together, what do you get? So let's kind of look and see. Well, if I can get my pen to work. All right, so if we have x plus 1 times x minus 1, we can multiply that with distributive property like we did in the last lesson. So we got x times x minus 1, and then plus 1 times x minus 1. All right, so we've got x times x is x squared, x times negative 1 is negative x, 1 times x is plus x, and 1 times negative 1 is negative 1. So we've got x squared. You can see that these terms cancel and bring down the negative 1. So in diagram 1, this represents x squared minus 1. All right, diagram 2, that's the one where we had x plus 2 and x minus 2. So if we have x plus 2 and x minus 2, we're going to have x times x minus 2 plus 2 times x minus 2. All right, so we got x times x is x squared minus 2x plus 2x and then minus 4. And again, you can see the same thing happens. The negative and the plus, they cancel the middle terms, and we got x squared minus 4. So diagram 2 was x plus 2, x minus 2. And when we multiplied that, we got x squared minus 4. Now, this one was x plus 3, x minus 3. So we know that we're going to start with this. And let's go ahead and see if it works in the same way. All right, so we got x plus 3 and x minus 3. So we're going to do x times x minus 3 plus 3 times x minus 3. So we got x squared minus 3x plus 3x minus 9. And again, you can see we've got x squared minus 9. So the middle terms, plus 3x and minus 3x, cancel. So that leaves x squared minus 9. So all of those work the same way. Minus x and plus x, negative 2x plus 2x, minus 3x and minus 3x, they all canceled the middle terms. All right, it says choose the correct words to complete the statements. The first term of each polynomial is squared. Is the square of the first term of each factor. And that is true because x times x is x squared. The second term of each polynomial is the opposite of the second term of each factor. All right, so this term is this number squared but it's opposite the sign because you got a plus and a minus, which gives you a negative. All right, so the first term squared, and then the second term squared, and opposite sign in the middle. All right, use the algebra tile diagram to explain why there are no x terms in the polynomial. All right, so if you look here, you can see that there are plus 3x's and minus 3x's, and so those cancel. So in each one of these diagrams, you can see the plus and the minus, 2 plus and 2 minus, and 3 plus and 3 minus cancel out. So even in the diagram, it does show that those cancel. And my pen is not working well today. All right, so with circles in the middle of the page, which of the following is a rule that generalizes the result from the table for finding the product of a plus b times a minus b? All right, so a plus b and a minus b is going to always produce a squared minus b squared. This is very important. You will see this in all of your classes, and if you learn this fact, it's going to be helpful down the road, even as far as the ACT. It's one of the most important things on your ACT. When you're a junior, everyone takes the ACT, but this is something I would put in my notes, and I would try to commit to memory. So you got a plus b and a minus b, and that's always going to equal a squared minus b squared. So basically, when you have the same binomial and the different sign in the middle terms cancel and leaves just a squared minus b squared. Okay? This is called a difference of squares. All right, that's all for task 1. If you have any questions, let me know. Lesson 15.3, task 2. All right, so we are analyzing special products. So here's another special product to consider. So consider the square with sides of length a plus b. It is divided into smaller squares and rectangles. So you've got a plus b times a plus b, because we know that a square has equal side lengths all the way around. All right, so it says choose the correct words to complete the statement. Area 1 is a times a, so that's a squared. Area 2 is b times a, or a times b. Area 3 is a times b. And area 4 is b times b, which is b squared. All right, which of the following represents the area of the square with sides of length a plus b as a polynomial in standard form? All right, select all that apply. All right, so we're going to have a squared plus b squared, and then we have twice ab. That looks right to me because both of these terms had BA and AB. You can use commutative property, but these middle terms are the same, so you're going to have twice that. So we've got a squared plus 2ab plus b squared. All right, this one would not work because it's not twice the middle term, but this one would also work, b squared plus 2ba plus a squared, because the squared term that starts doesn't matter. Again, commutative and associative property, you can rearrange these, but it does have to have twice the middle term. Which of the following is a rule to finding the product a plus b squared? And that would be the last term, which we just looked at. So anytime you have a binomial squared, meaning a binomial times itself, because as we looked at with the picture, you've got a side times a side length in a square. The sides are the same. So you've got a binomial squared, and it's always going to equal the first term squared plus twice AB plus the last term squared. So your middle term will always be twice when you've got a binomial squared. So it's slightly different than in the last example where the middle terms canceled out, but that was because they had different signs. This one, the binomials would both have a positive sign. All right, that's all for task 2. If you have any questions, let me know. Lesson 15.3, task 3. Find the product of a sum and difference. In task 1, you discovered the following rule for multiplying a plus b times a minus b. The result was a squared minus b squared. It is called a difference of two squares. So when you have a sum and difference pattern, you've got a plus b times a minus b. That equals a squared minus b squared. Okay, again, that's called the difference of two squares. All right, a mathematical justification of the sum and difference pattern is shown below. A plus b times a minus b. So you do a times this binomial, and you do b times this binomial. That's distributive property, which we've been practicing. All right, so when you do distributive property, you get a squared minus ab plus ab minus b squared. You can see that the middle terms equal 0, so it cancels, and it leaves a squared minus b squared. So now we're going to do an example. It says multiply x plus 4 times x minus 4. Same binomial, different signs in the middle. You're going to square the first term and then square the second term. So it's going to be x squared minus 16. So you can kind of skip the middle step. You don't have to do distributive property if you recognize this is the same binomial, different sign. All right, so it says explain why the sum and difference pattern can be used to find this product. Because any binomial that's the same binomial, different sign in the middle, is going to fit this pattern. That's why the general rule is a plus b times a minus b equals a squared minus b squared. As you've practiced these, if you want to do it the long way still, just to make sure that you get the practice and you get the right answer, that's fine. But as you move through these, it's important to learn that these special products are always going to work this way, and you can get to the answer quicker, which sometimes is a good thing, because like on the ACT and EOC, which are timed tests, that's important. So let's look at this one. Same binomial, different sign in the middle. So we're going to square the first term. Negative 4x squared is 16x squared, and then negative 9, because 3 squared is 9. And the reason this is positive, a negative times a negative is a positive. So a negative squared is the same thing as a negative times a negative. So it says, why is the coefficient of the x squared term positive? The square of a negative real number is a positive real number. The coefficient of the term with the variable is always positive. Okay, this can be positive or negative, but if you square it, it's always going to be positive. All right, if I multiply x squared plus 5 times x squared minus 5, again, same binomial, different sign in the middle. I'm going to square the first term. X squared is x to the 4th. Remember, a power to a power, you multiply. And then 5 squared is 25, so x to the 4th minus 25. And you can see that it's always going to have a negative in the middle. So a squared minus b squared. Choose the correct expressions to complete this statement. The expression x squared replaces a in general. You can see here, a is the general form, x squared takes its place, and the expression 5 replaces b in the general form. So 5 is in place of the general form. All right, and one last thing. Again, it's called a difference of squares. Difference means subtract. So you can see a difference of perfect squares in math. Usually the name is directly related to what it is. And in this case, you have a perfect square minus a perfect square. Again, this is called a difference of squares. If you have any questions, please let me know.